Welcome to Chemistry, Semester 2. Okay, we will be starting in our nice free online textbook with Chapter 10, talking about the condensed phases and their properties. That is to say, we'll be talking about solids and liquids. Now, if it's not a gas phase, then it's a condensed phase. Okay? So that's why we call them condensed phases. It's because they have been condensed. They've made more dense. They have come together. Okay? You'll recall, hopefully, but kinetic molecular theory says that a gas is composed of lots of particles moving around, not interacting with one another, with tons and tons of empty space in between them. A solid and a liquid have become more dense. That empty space is no longer available. Okay, the particles are all touching, and the solid and liquid, the particles are interacting a great deal. That's why they have condensed. That's why they are in the condensed phase. It's because the particles are interacting. They're attracted to one another. They want to be close together. So, looking at the properties of liquids, what we're seeing here, some of the properties are surface tension, capillary action, viscosity, and vapor pressure, are very heavily involved with the intermolecular forces of liquids, the fact that the particles are attracted to one another. Okay? So we'll start with surface tension. Now, imagine that you have, a droplet of water. Okay? There's that great big droplet, and these are the particles of water inside that droplet. I'm drawing them extra big just to make them easier to see. And I'm putting space in between them as artistic license. Now, this particle here in the middle is attracted to all of the other particles around it. That, incidentally, is why droplets form spherical shapes. Those forces, those intermolecular forces, go out in all directions. They're nice and uniform that way. And they want to get as close together as possible. And the only way to do that, to minimize the space between all the particles, is to form a spherical shape like that. That's pretty much the same reason any real special effect in outer space is going to be, spherical. Now, at the surface, you get something similar. Okay, you see here a particle at the surface. It's attracted to everyone nearby, but of course, the half of the space that it sees is just empty space. There's no other particles nearby. So it's very unhappy. Okay? A surface effect or edge effect, boundary effect, usually means unhappy particles. So for these particles on the surface of the liquid, they are quite unhappy. And so they're trying to basically burrow their way inside. Problem is, there are other particles in the way, so they can't. So the surface of the liquid usually experiences a greater sort of forces, and they're only pulling in one direction. All of which is why you get that well-defined, sharp surface at the edge of a droplet of liquid, or a bubble, going in the other direction. So when you have something come down onto the surface of a liquid, let's go ahead and draw it, nice and flat here. It exerts a force downward, and you have this layer of very unhappy particles that greatly resent that intrusion. And so they are going to push back against it. So that's why, water striders can skate along the surface of the water. Their minuscule insectile weight is not enough to break that surface tension. If you're really, really careful, you can float a paperclip on the surface of a glass of water. Not the most interesting, science fair experiment, but, you could do it. So that is surface tension, and that is why you get surface tension. It's because of those intermolecular forces. The particles want to be as close together as possible. And for our next property, we have capillary action. Now, your book will ask you to do math for this. I personally won't, because I find that major mega boring. But, it's there for those of you who want to be engineers or something. Capillary action. You may have noticed, if you put a droplet of water on a surface of some kind, glass or a tabletop or, the inside of your little brother's ear, it doesn't necessarily always behave the same way. It can either bead up on the surface or it can wet the surface. Okay? Beading up means that it doesn't like the surface. Okay? The particles of the liquid like each other more than they like the surface, so they pull away from it. So they form that nice round bead, like water on glass or on a waxed floor or waxed car. Wetting is what happens when they do like it. So they spread out on the surface. They're still going to form, sort of a somewhat spherical shape. They're still trying to reduce the amount of surface. It's a competition between how much they like the surface they're on versus how much they hate being spread out. So those are what you see. Now, if instead of putting the water, or the liquid, I should say, on a flat surface, if you put it inside of a narrow tube, you're going to see something similar. It can either bead up, that is to say, it'll form this upward hump, like mercury inside of a glass tube will do that, or it can try to climb the walls. It will still be wetting the surface of the tube, but it'll be vertical, so it'll be trying to pull itself up the walls instead of spreading out on the flat surface. So you get the inverted shape there. Those are the meniscus that you're looking for when you measure something inside of a graduated cylinder, and that's why you can get the downward pointing meniscus or the upward pointing meniscus. It's because of the attraction between the particles of the liquid and the particles of the tube that they're in. If the tube is sufficiently narrow, then you can get capillary action. Capillary refers to just a very, very narrow tube. And the action refers to the fact that you can actually get a push or a pull on that liquid. So if you have this positive meniscus over here on the left, like mercury inside of a glass tube, it will actually, the capillary action will actually push the liquid down. Because the mercury is trying to get away from the glass walls of the tube, or whatever liquid and whatever tube you have. It's trying to get away, so it'll actually go down away from the neutral zero level of the surface of the liquid. Conversely, if you have this other meniscus over here, water inside of a glass tube, it'll try to climb the walls. It'll actually pull the liquid up the walls. And how far away from the zero line the capillary action will get you, that is based on how strong the interactions are between the particles of the liquid for themselves, and the particles of the liquid with the walls of the tube. Stronger interactions with the walls of the tube will lead to greater capillary action. You also have the issue of the narrowness of the tube. You get greater capillary action for a narrow tube, and that's just because it's the square law. As you increase the diameter of the tube, you're going to increase the amount of water inside the tube faster than you're increasing the size of the walls of the tube. Okay, the surface of the water will go as the square of the diameter or radius of the tube, but the amount of wall of the tube increases linearly, directly with the radius of the tube. It's pi r squared versus 2 pi r. So the effective capillary action goes down very rapidly as you increase the size of the tube. And that is capillary action. It's based upon cohesion versus adhesion. This is an important thing. Oh, I'm glad I glanced back up at the notes here. Cohesion is the attraction of the particles of the substance for the other particles of the substance. Adhesion is the attraction of particles of different substances. So a droplet of water is spherical because of cohesion. It wets onto a glass surface because of adhesion. Okay, so that's important. Next up, we'll look at viscosity. Okay. Viscosity is the resistance of a fluid to flow. Fluids don't necessarily want to flow. An object at rest wants to stay at rest, right? It's sort of an internal friction for flowing liquids. Viscosity can vary widely between substances, such that water actually has a very low actually viscosity. You pour water out of a bottle, it'll flow very quickly, rapidly out of the bottle and onto again your little brother's head. Whereas honey or syrup have fairly high viscosities, and then you have something like pitch. Um, Pitch, used to be used as a sealant. It's made out of pine tar, and it is technically a liquid, but it flows ridiculously slowly, so slowly that they actually set up an experiment where they put pitch. They couldn't really pour it. They just placed it in a funnel and waited for it to form a drop, and then for that droplet to fall, and then they timed it. Problem is that they kept on messing up the experiment because it took a couple of decades for the droplet to form and then to fall into the glass beneath the funnel. Eventually, they set up a video camera and finally got it, and people around the world went, "That's vaguely interesting." Not incredibly interesting. In any event, viscosity varies with temperature. As you increase the temperature of a liquid, the viscosity will go down, meaning that it will flow faster. A hot liquid flows faster than a cold liquid, like molasses in January, right? It's a molasses, is a syrup made from cane sugar, sugar cane, and it is very viscous. And when it gets cold, it flows very, very slowly. At higher temperatures, boiling molasses will flow quite quickly. It'll still be sticky though, so it's nasty. Got to be careful with it. Okay, and next up we have vapor pressure. Vapor pressure is another thing where they show you some math. I am going to avoid the math on this one. Just know that vapor pressure is, again, related to temperature. And this is how. Recall from kinetic molecular theory that particles are in constant motion, always moving in random directions. Well, that's still true for condensed phases. It's just that they can't move very far because there's always something in the way. Unless they're heading toward the surface. In which case, you're suddenly looking at the biggest game or red rover ever. The particles near the surface are trying to break out, and the other particles are holding them back. So what matters then is whether or not they have enough energy to escape. And higher temperature just means they're moving faster. They have more energy. So the higher the temperature something is, the more likely the particles of that liquid are going to be able to escape from the liquid and into the gas phase as a vapor. So higher temperature means that more particles are escaping from the liquid as a vapor, and thus the liquid is exerting a higher vapor pressure. That's what vapor pressure means. Okay, how much of that liquid is a gas above the liquid. Right? So higher temperature, higher pressure. Lower temperature, lower pressure. Fairly simple. And that is what eventually causes boiling, when the vapor pressure of the liquid is equal to the pressure of the atmosphere pushing down on the liquid. So those are the properties of your liquid phase materials, your surface temperature, and capillary action, and viscosity, and vapor pressure. Now, obviously, there's more to being a liquid, and each of these can be discussed in much more detail. But that is all the detail we are going to go into for those. And we are getting on to close to 15 minutes, so I'm going to go ahead and call it for this video, and we will pick it up again in our second video.